This is the sine function tutorial. The sine function can be written as y is equal to the sine of theta. The easiest way for me to explain the sine function to you is going to be through the use of graphs. Here's what a typical sine function looks like on a graph. I'm also going to bring in an image of the unit circle here to help with this explanation. Any point located here on the sine function, so any point along this wave right here, is going to correlate directly with the y value of an angle in standard position on our unit circle. So if I had a point here at the top of our sine value, so let's say this point right here, that's going to correlate directly to the value of y of an angle in standard position over here on the unit circle. So remember, standard position is when an angle is formed where one ray of that angle lies on the x-axis, like I've drawn here in red, and the vertice of the two rays joining each other to make that angle lies at the origin of this unit circle, or of our coordinate plane here. So if I were to draw another ray straight up right here, this point where this ray, the terminal side of this angle in standard position here, that point where it intercepts the unit circle, the y-coordinate of that value right there correlates directly with the y-coordinate over here on this sine function. So let's take another look at one of these points. Let's take a look at this point right here on this sine function. If I were to draw a line directly across here to the imaginary unit circle off to our left, that point that I indicated here with the arrow on that sine wave is going to correlate exactly to the y-coordinate of the point right here where this angle in standard position, so if I made theta here, this is the angle in standard position, the y-coordinate of that intersection point of the terminal side of that ray passing through the unit circle is going to correlate directly with the y-coordinate, so the y value of that point right there, and so on and so forth. If you just drew lines directly across, relating these two, you'd see that the pattern would go up and down like this. For example, look what happens if I choose this point right here. On our sine function, I'm going to draw a line connecting directly across to our unit circle. Now take a look at this line and notice that this point right here on the unit circle, the y value of that point is going to correlate directly to the y value of that point on the sine curve over here. So if you were to draw an angle in standard position, you'd have that original ray right here along the x-axis, and then you'd have another ray joining it right there at the origin of our coordinate plane. So this would be your angle in standard position. Remember, for standard position here, if you wanted that to be a positive angle value, we'd have to go counterclockwise. Now, if you chose a point over here on this side of our sine function, it's going to correlate to a value directly over here on this side of our unit circle. And as you go all the way around our unit circle like this and correlate points, so if I were to go counterclockwise like usual around our unit circle, those values would coordinate directly just like this. At that same time as you're going up and left on the unit circle, you're going up and right on this sine function. Then you go down, and that's correlating to this region over here. You go down along the sine function. You max out at the bottom, so down here on the unit circle at -1. Then you start to climb up and right again. And that's you climbing up and right again on the unit circle over here. And you continue on doing that as you make rotation after rotation around the unit circle. That sine wave is going to go on forever to the left and right. And it's just correlating exactly to making rotations over and over about that unit circle, up and down, left and right, that kind of thing. Now I'm going to clean up these graphs a little bit, and we're going to actually apply that to some problem work. Now that you can see how they correlate together, the unit circle with an actual sine function. And if you put a sine function into your calculator, so just y equals sine x in your calculator's graph utility, and then watch the graph, it's going to look just like this curve, but again, it's going to go left and right forever in both directions. And you'll be able to apply that to what we're doing here with these problems. Alright, so the question is, what is the value of y equals sine theta when theta is equal to 90 degrees? Well, if you find 90 degrees over on our chart here, so 90 degrees over on our sine function, 90 degrees, if you go straight up, correlates right here to this position. And if you go straight across that dotted blue line, you'll find that the y-coordinate, that value there, is 1. So the value of y equals sine theta when theta is equal to 90 degrees is 1 unit. If our unit circle were in meters, it would be 1 meter. If it were in feet, it would be 1 foot. Now what about when theta is equal to 360 degrees? Well, again, we'll come over here and look at 360 degrees on our sine function. At 360 degrees, our sine wave here in orange is just passing back through the x-axis. So the y value of our graph as it's passing through the x-axis is going to be 0 right there at the x-axis. So when theta is equal to 360 degrees, our value here for the function y equals sine theta is 0. So whenever anyone asks you what the value of a function like a sine function here, y equals sine theta, is at a particular measurement, like let's say when theta is equal to 90 degrees, just go ahead and look on your sine function, find where the graph happens to be at 90 degrees. On your calculator you could trace along there, and then correlate that back to its y value on the graph. Now let's go ahead and do the same kind of problem, but if our graph weren't in degrees, if it were in radians. So here's what our graph would look like if it were in radians. We'd change out our measures of 1, -1, that sort of thing over here on a unit circle to 2 pi, pi over 2, pi, and 3 pi over 2. Now remember, this value here is either 0 or 2 pi depending on how you look at it. If you were to do a full rotation about the unit circle and come back here, then you've gone 360 degrees and a total value of 2 pi. This value up top here, pi over 2, is just 1/4 of the distance around the unit circle, and the distance around the unit circle is 2 pi units. So 1/4 of 2 pi is pi over 2. Now notice on our sine function graph over here, we've also changed out these units. 90 degrees now is pi over 2. Where 180 degrees was, we have pi. Where we had 270 degrees before, we have 3 pi over 2. And where we have 360 degrees is now 2 pi. Those are representative of those 90-degree turns about the unit circle. We've cut that circle into fourths again. So we'll go ahead and drop in our sine curve. Our sine curve doesn't change simply because we're looking at our graph in terms of radians instead of degrees. It's just a matter of how you're looking at it. But it's still making those same turns. It makes that first curve at 90 degrees as it starts to travel down the back side of the unit circle again. It travels downward. It hits 0 again on the y coordinate when it hits the x-axis again. Remember, these values over here on our sine wave just correlate directly to the y values over here on our unit circle. So when we're hitting the x-axis here, here, and here, that's just us hitting the x-axis here, here, and back again as we go back around the circle. So if I were to ask you to use the above graph to estimate the value of these sine functions, you could. Let's begin with that 3 pi over 2 radians. Now remember, we just go over to our sine function here to the location of 3 pi over 2 radians on that graph, and we're going to go until we find where that value, that x value, matches up with our sine curve. And we take that y coordinate there of where that graph is, that sine curve, and that's our value of the sine function at 3 pi over 2 radians. Because remember, the sine function is looking at the y value in correlation with our unit circle. So down there at 3 pi over 2 radians, that has a value of -1 because it's the bottom of our unit circle down here at the bottom. So this value would be -1. -1 unit depending on the size of our unit circle, whether it's in meters, feet, centimeters, whatnot. Now let's take a look at the problem on the right. They want us to estimate the value of the sine function at 6 radians. Well, remember that the distance around the unit circle is 2 pi radians, and pi is roughly 3.14. So 2 times 3.14 is 6.28. So you could say a full trip around the unit circle would be 6.28 rads, or radians, whichever you prefer to say. And they want us to go around 6 radians, so almost a full trip around the unit circle. If we started here at our origin, and we traveled around the unit circle, if the whole thing is 6.28 rads, and we only want to go 6 rads, I'd stop a little bit short of our full trip around the unit circle. Then you could draw a line directly across over to your sine function here. Remember, we're on the back side of the unit circle, so we're going to land over here, and this y value would be the answer. Now, to get the exact value, you could go ahead and plug that into your calculator. You'd have to switch the mode of your calculator into radians, and then you could just do sine of 6. If you did that, you'd get a value of negative 0.28. If you wanted to just leave your calculator in degrees, you'd have to convert 6 radians to degrees. And remember, to do that, you'd simply multiply it by 180 degrees over pi. If you multiplied it by 180 over pi, you'd get 343.77. So remember, a full trip around the circle is 360 degrees, and you went 343.77, which is roughly about here. So if you left your calculator in degree mode and just did the sine of 343.77, you'd get that same exact value, negative 0.28 roughly. Alright, so now that you have a basic understanding of the sine function, let's go ahead and take a look at some of the properties of the sine function.